Okay, our clock says 8 a.m., so we'll get started on this Thursday. Good morning, stats.
Good morning.
Okay, that's a pretty good orienting response. I know it's early, it's only 8 a.m., and we're usually here at 8:30, but that's the way we like it. Right? We like to start nice and early because we're that enthusiastic about stats. And we're that enthusiastic in general about science. Today is a big day for science. How many of us are going to be doing a summer science poster today? Okay, so several people in the room are doing a summer science poster, and if we have a moment later on, maybe we'll get just a little preview on those, but we might not have a moment later on, and more on moments in a moment. But I look forward to seeing your posters at 11:45. That's going to be in the Curtis Veggie Hall. We do that on the first Thursday of the semester each year. Of the first full week of the semester, I should say. So from 11:45 to 1:15, we have that session going on, and I look forward to seeing lots of psychology posters and learning a lot about psychological science and all the other sciences as well. Then also today, just as a reminder, we have another big event on the Thursday of the first full week of classes. Starting at 4:30, we have the campus activity fair. And how many people have a table of some variety? Okay, can we just get some notion of what's going on in your tables?
I'm president of Women's Club Volleyball. So.
Women's Club Volleyball, okay. Anybody? I saw lots of other hands, yeah?
Breakaway trips.
Breakaway trips, okay, so, yeah.
There's going to be the vegetarian and vegan club.
Okay, the vegetarian vegan club. They're out doing their thing. Go ahead, Jake. Club soccer.
The Pan-Hellenic Council.
Pan-Hellenic Council.
University Programming Council.
University Programming Council.
Share.
Share? And did you have one? Or you
I'm treasurer / vice president of Women's Club Volleyball, and I'm going to be in the first generation.
What was the other one?
The first generation.
The first generation table. Very good. I'm sorry.
Big Brothers, Big Sisters.
Okay, Big Brothers, Big Sisters. So lots of things going on. We're a very active campus. Okay, so looking forward to seeing you hopefully at 11:45, somewhere in that mix as we're looking at the science posters, including psychological science, and then maybe at 4:30 as we're all checking out each other's tables for student activities. Just in case I run out of time, I always want to make sure that people are okay with what we're doing for the very next time. So people always have complete clarity. So I like to put this up on Blackboard. This is what you'll be doing for tomorrow's session, and that'll be at 8:30 tomorrow, okay, rather than at 8 a.m., and that's just our Monday, Wednesday, Friday schedule. We have another bunch of TED Ed questions going on there, and we'll be doing an introduction to hypothesis testing. Some of this will be review for many of you because there are many themes that we touched on here in Psych 200, but it's nice to get a review, and there are also a few new ideas there. So hopefully you'll see something old and something new in almost every one of our sessions throughout the semester, because we are building on Psych 200, but we're taking it into new directions also. Okay? Thank you all for your responses on TED Ed. What I thought I'd do is start us out today by talking about something called the moment. And you may or may not have heard this phrase before. How many people have not heard of the statistical vocabulary word moment? You've not heard of it before, okay? That's fine. Have you heard of it, Gwen, or you hadn't heard of moment before either? Okay. So the notion here is that we can use this idea of the moment, or this word moment, to describe the shape of a distribution. And the reason I'm bringing that up this morning is we spent most of yesterday talking about frequency distributions, and we had some TED Ed questions on that. So in statistics, a moment is a quantity that describes the shape of a set of points, and that can be any set of points, but in our context, it's usually a frequency distribution. Okay? And in lay terms, we can say moments typically describe frequency distributions mass, interestingly enough. And we'll see in a moment that's just nothing more than the sum of all the possible scores. By the way, this is available to you on the S drive. You don't have to take this down note for note. If you dial out onto our S drive and go into the resources folder, this is available. Okay? And so we have the mass, which is really going to turn out to be the sum of all the scores. And then as we talked about yesterday, the two major descriptors that we get in descriptive statistics are going to be some kind of central tendency, mode, median, or mean, some kind of dispersion. We talked about different varieties of dispersion. And then yesterday we began to grapple with other elements of a distribution shape. And one of the ways that the distributions can differ from each other is skewness. We talked about kurtosis, this weird idea about the heaviness of the tails. You might also think of it about the peakedness of a given distribution. And then there are different kinds of descriptors also. We might call them higher order descriptors. But usually these two are what you get. And that's basically expected in any psychological science journal. We always want some indication of central tendency and dispersion. as we get up higher into statistics, we can think about such things as skewness and kurtosis, and potentially other variables as well, although we wouldn't be doing other variables in this course. We'll occasionally be talking about these two. We will always be talking about these. Okay? So just to give you some idea about a little bit more regarding the definitions of moments, and I think you might find this somewhat intuitive, because if we think about some of maybe the first moment, okay, which would be something like mass, or we'll go with central tendency, we know that we have three different ways of describing central tendency. We have mode, median, and mean. Right? We also know that if we talk about the dispersion of scores, that was, if you will, maybe the second moment on our list, the dispersion can be something like the range. It can be something like a standard deviation. The standard deviation is based on a variance. Okay? Right? It's actually the square root of the variance. Who remembers making that distinction in Psych 200? There's between a standard deviation and a variance. Okay? Some of us recall that, some of us don't. Okay? We'll spend more time on computing variances and standard deviations in sessions coming up soon. Right, so you can have standard deviation, variance, standard error. You can have interquartile ranges that we talked about yesterday. So different ways of talking about dispersion, but you would want to describe the dispersion. Okay? Then there's skewness, and we talked about this, the negative skews and positive skews. You might be able to see it here. It's very, very faint. Can you see the second half of what would have been a Gaussian distribution shown here in gray? Okay? So I picked this up from Wiki and Wikimedia Commons, and so that would have been a non-skewed distribution, but we can have these skews. And then there are different ways of computing skew. One of our old buddies in statistics is Carl Pearson. He gave us the chi-square. He gave us the R value. Right? He gave us a lot of things. He also thought a lot about skewness, and he came up with these first two early definitions of skewness. He took the mean of a distribution, he subtracted the mode, and then took the standard deviation of that. I'm sorry, I think that's my typo. Pardon me. I think that's mean minus median. I'll save that, put that back up, okay? Mean minus median, and then the standard deviation of that. And he also thought, well, maybe you want to multiply that by 3. Okay, so you can see that there are lots of different ways of getting this. If you were to go out to Wiki, we don't have to do that now, you will see that there are many ways of computing skewness. So which one is correct? Well, they do slightly different things for us, just like it's the case that mode, median, and mean do slightly different things for us. They all might be describing something like the central location or the central tendency of that data set, but they're giving us different ways of thinking about central tendency or dispersion, or in this case, skewness. Okay? Here's another way of thinking about the moment, different definitions of moments, which again are speaking to the shape of these distributions. A moment of a random variable is just the expected value of the power of a random variable. So we're going to think a little bit about exponents, and just to make that clear, and we won't compute exponents today, but there's the zeroth moment, or the mass of the data set. And what we're going to do here is just add up all the data. I can point to it this way. We're going to add up every one of these, and the simple sum is our mass. Okay, that's how heavy the data set is. Okay, then we can do this. We can take each of those elements, okay, raised to the first power. That's not doing anything particularly interesting, and we can divide by n, and that gives us a mean. Okay, so this is a fancy way of talking about the mean. We just added this particular exponent here. The reason we added that exponent, even though that exponent isn't really doing anything for us, is it makes obvious the next component. And if we drop down to variance, okay, which is a first step that we take in getting the standard deviation, we can square any one of the scores in our set and then divide by n. Okay? And if we do that, we're getting some indication of the variance, or just how dispersed the scores are. Okay? Another definition of skewness, which was an idea that we grappled with yesterday and back on this slide, positive and negative skews, you can do something like this. You can take the third moment for skewness, and you can raise each one of the elements in your data set to the third power and divide by n. So it's, raise it to the something power and divide by n. These are all 3s. You can get an indication of kurtosis by raising to the 4th power and dividing by n. Okay? Sometimes you also subtract by 3 here, interestingly enough, to give you numbers that are going to be varying around 0. So negative numbers are going to have platykurtic distribution. Positive kurtosis values will have a leptokurtic distribution, and so forth. And there are still other ways of computing kurtosis. Okay? But so the idea here is that we're trying to describe the shape of distributions, and we have these different moments, these different characteristics. Okay? You can continue with this pattern, and you can get to 5th order, 6th order. There's no end to those. You might ask yourself, though, what would that tell you? And it might be that in a particular scenario, something really interesting happens at the 5th power. There's something about the ratio of the median to how extreme the tails are, something along those lines, right? But generally, we use we always have to sum up the set. That's sort of a given. That's the 0th. And then we use central tendency dispersion. And occasionally, we use skewness and tail thickness. Okay? Lots of different ways of defining those. And statisticians call those moments. Okay? That's a little summary of another way of thinking about what we were describing yesterday. Who's okay with all that? Does that work for us? Okay. And it's out on the S drive. Okay. Okay. Speaking of all these frequency distributions and their shapes, can we do an exercise? We haven't been into SPSS yet, so I wonder if we can go to SPSS. On our first day of class, we checked to see if SPSS was there, and it wasn't. And then we found out that SPSS was there. So if you need to move to a place where you can get onto SPSS, please feel free to do that. I've got SPSS open, and I'll use a data set that I like to use in Psych 200 just to get today's conversation rolling in SPSS and building on the momentum that we have from yesterday on frequency distribution. So if you can open up SPSS, and if you can navigate by going File and Open, and we'll go to Data, I'll leave that there so that you can get that far with me. And when you get that far, maybe you can raise your hand. You can click on Data. I realize SPSS is slow in opening. And I get the sense it's even slower the first time that you do it. I think it goes through some startup procedures, because mine came up a little bit more quickly this morning than it did yesterday. So I'll give you a moment to go that far. We're going to open up a .save file in a moment, but I'll give you your computer a moment to catch up with us. And that's File, Open, and Data. That's what we want to click on. Okay? And you can click on Data. And then we're going to go and do some navigation. Okay? And I've dialed in there already. If you can go to Look In, and we can go to something like Computer, and we'll go to the S drive. I'm Matthews. Okay, we'll go to Psych 370 and the resources. And hopefully, we will have a GSS 93 subset folder file there, .save. How many people find that? Can you already? Okay, and if you can click on that and open it up, away we go. Some of you may have used GSS 93. Some of you might not have. Right? It's an older data set, but it's available to us for free. And by show of hands, how many people had that open? Okay. Oh, is yours still coming up? Sorry. That's right. Yours. You're okay. So I'll just, as Gabby's computer is coming up, I'll just give us a little bit of background on the GSS. There's a group of social scientists that conduct the General Social Survey. I believe they're located at the University of Chicago, and they conduct a survey either every year or every so many years. It's probably financed by something like the National Science Foundation, and they ask lots and lots of questions of a random sample of Americans. And this happens to be what they've made available to us from way back in 1993. Some of you probably weren't born when this was being taken, but anyway, it's a great data set, and it gives us a snapshot of what was going on in the U.S. Back in 1993. So you can say open, and we'll see if Gabby's computer's caught up or not yet. Okay. Okay. I'll point up here so you can see as yours is still coming up. You might remember that SPSS has a data view and a variable view. Can you all click on those too? And for Gabby, I'll click along, so as if she were doing this. Right? Data and variable views. Okay. And if we think about the variables, we can ask, what do these researchers have in mind? What kinds of questions do they want to ask? So can somebody tell me how many variables were in this data set? Okay, thanks, Melanie.
96.
Okay, Melanie's got 96, and the way that she found that, I think, is by dialing down. And I realize that everybody's used SPSS before. Sometimes you use it a lot, but you can see they've looked at 96 different variables. So if this is some kind of survey research, then this particular survey might have had as many as 96 questions. Okay? Can I see if you can pull this answer out too? So we have 96 variables. How many people were in this particular sample? I want you to think about that. Poke around to see if you can find them. When you think you have the answer, can you raise your hand? We'll see how many people can get there. Vanessa's got, okay, lots of folks are getting there. So remember that you can poke either on the variable view or the data view. And the question on the floor is, how many people are in this particular sample? We know that these people were sampled seemingly on 96 variables, I think we just said. How many people were sampled? Hands up if you think you've got the answer. Okay, I think I saw Vanessa's hand go first. What did you come up with, Vanessa? 1,606. Let's see where you came to on that number. So I'm going to go over to variable view. I'm going to drop all the way on down. And, okay. You know what it is? I think they've got 1,500 cases here. I think I see where you're getting at. Okay, but I think they have 1,500 cases. Now remember that in SPSS, and this is a bit of review, a case, you can think of that as a person. I don't like to think of it though as a person because it could be a rat. Okay, right? It's you have a case. It's a type of information set. Often it's what you have on that one person, that one participant, and that goes in the rows, and then we have the different columns corresponding to the different variables. I think I see a question coming from Victoria.
Oh, no, sorry.
Oh, okay. I thought I saw a confused look and a hand going. Okay, all right. So we have 1,500 people in the sample, and we've asked all of them 96 questions. Doesn't mean that they responded to all 96 questions, okay? But they might have sent the survey out to all those folks. That's a pretty hefty data set. Has that come up yet, or is that still moving slowly? SPSS is loading. Okay, so it did take a while. So thanks for bearing with us. Okay. Okay, a couple of other ideas. Can somebody tell us about what's going on here over on the measure side? You might remember looking at measures back in PSYC 200. So we're in variable view, and we have a measure column. Somebody remind us of what that was all about? The measure. So what is going on in this column? What's the measure telling us? Oh, yeah, thanks.
It's telling you what type of variable it is.
Okay.
Scale or ordinal, rank, or nominal.
Okay, right. So, and it's giving us basically three choices, right? And the three choices are nominal, and we can think of that as categorical. So in some of the examples that we had yesterday, I think we had some examples of different majors or different courses, and it was psych and bio and history and English and so forth. Those would be nominal variables. Categorical variables, we can do chi-squares on those things. Right? We can statistically compare qualitative information. It's an interesting idea, right? So people talk about quantitative analyses, they talk about qualitative analyses. You can do a quantitative analysis on qualitative variables by using something like chi-square. Okay? And you just do frequency counts. How many psych majors do you have versus how many bio majors do you have? That kind of a thing. Okay? Then there's the ordinal type. And then there were two other scales. One was called an interval scale. One was called a ratio scale. In SPSS, they combine those two and they treat them as one variety. And a little bit unfortunately, a little bit unhelpfully, they call that scale. Okay? So the interval scale and the ratio scale are called scale variables inside of SPSS. You probably had all of that in Psych 200. Who remembers that much from Psych 200? Does that sound okay? Good. So that is a little bit of review. Okay. Can somebody help us out with the distinction between labels and values in SPSS? Labels and values. Okay. Sarah's got something.
Labels are like the names of the different variables that they were tested on or asked about, and the values are the possible scores that they could have.
Okay, really good. So this is just a little bit confusing. SPSS has a few different ways of referring to a variable. A variable has a name, and the name has certain kinds of rules associated with it. For example, one rule is you can't have spaces in here. It has to be only a certain number of characters. I think you can't lead with a special character. I think you can't lead with a number. There's a bunch of rules about what the name of the variable can be. But then you can put in something that's a label that's way more helpful. You can have a good portion of a sentence in there that has spaces, and it really unpacks what it is for you. Okay? And then you might specify the values that this can take. So it might be that you could choose to encode psych, bio, English, and history as 1, 2, 3, and 4. Okay, so that when you're typing away and you've got lots and lots of data, you can say psych 1, bio 2, psych 1, bio 2, right? You have to put in a single number rather than the entire phrase. Okay, so that's a fast way of getting the data entered if you're doing some kind of manual entry. And some poor soul does have the unfortunate job frequently of doing some manual entry somewhere, maybe into Excel, maybe into SPSS, and it can help those folks if they just have a simple numeric label, right? Okay. Okay, so that all looks good. Anybody have an idea about what's going on over here in type? Type of variable. It always defaults to numeric. Can anybody think of some other usages that we might have there? Okay, well, you can occasionally use something called a string variable. In fact, you can use any of these, but occasionally we might be using string in here. And a string variable is a variable that will allow you to put in as a value something like a letter. Okay, so it might be the case that we make a participant ID a string variable, and your participant might be P1 for the first participant, P2 for the second participant, and you can begin entering P1 and P2 and P3 into your data set. Okay, but if you were to do that, you'd have to define that variable as being a string, because normally over here in data, we get numbers. Okay, SPSS clearly is a statistical set, and it's used to having numbers as data. Okay, you can put in letter values as data, but you would have to define that as being a string. And we'll do some examples of those, but that was just one other field I wanted to call to your attention. Okay? All right, so with that as practice now, why don't we get over together to the data view screen, and we'll see if Gabby's is still coming up, or if you're on board now. Okay, very good. Okay, and we now have this data set that is the General Social Survey, taken way back in 1993, probably by the folks at the University of Chicago. They're sampling randomly, and these folks are on it. They really know how to get a random sample. Okay, so they're getting a random sample of Americans back in 1993, and they have all these variables. So what I'd like to do is see if we can generate some frequency distributions. We talked about those yesterday. We just talked about moments, how these are differently shaped. Let's get some frequency distributions on what many of my students find to be a fun variable. So if we go back to variable view just for a moment, there is variable 4. I think the students through the years have gotten a kick out of this thing. And this is the variable that has a label age when first married. Okay? Let me shrink that down a little bit. Okay? So age when first married. And you might think about, well, what would that distribution look like? Right? You just to think broadly about it. And we can get some detailed information about that by going analyze. Okay? If we want to get a frequency distribution, maybe you remember from Psych 200 because you do these there. What's my next one to click on to get a frequency distribution? Oops, sorry. Analyze. Descriptives. Okay, so it's a descriptive and typically we're looking for central tendency and dispersion. Okay, and we'll spend more on time. Why don't we go to analyze descriptives, and we'll go to something like frequencies. Okay, and what I'm going to do, I was in here earlier this morning, I'm going to dial down to the 4th variable, which means I have to click on the down arrow 3 times. I'm starting on the first variable, I go to the 2nd, 3rd, and 4th variable, and I'll slide that one over. So we get age when first married. Okay? How many people have that? Okay, real good. You may have done something like this in Intro to Psych, but let's go to the statistics button, and you can see I was in here earlier. Let's click on all of this. Let's get some percentile values. And I took cut points at 10 equal groups. Because this was 1993, I'm going to say, I wonder what the 93rd percentile was back in 1993, but you could put in any other percentile that you wanted. So I put in a 93 there. I took all different kinds of measures of central tendency, mean, median, and mode, also the sum, which we called the mass earlier today when we talked about moments. Why don't we click on all possible kinds of dispersion, and we'll click on these 2 other moments, these slightly higher order moments. We'll click on skewness and kurtosis. Okay, so we've clicked on just about everything. We will not click on values or group midpoints. We might come back to that at some later point. Okay. Who's okay with that? We have just about everything on that screen clicked except for this guy. Okay, and I put in 93 somewhat arbitrarily. Okay, okay, we'll click on continue. And then we also click on charts. And we'll get a histogram to build on yesterday's conversation and to give us a visual representation of the moments we were describing just a little bit ago, and we'll show the normal curve on top of that. So it will give us a frequency distribution and it will impose a normal curve or a Gaussian curve, even if it doesn't fit particularly well, and we'll click on continue. Okay? And people have all of that? Okay, why don't we click on OK? And we'll dial down to that, and I'll make that larger. Here's our title, notes. Okay? Okay, why don't we take a look? I'll give you a moment to look through age when first married. Okay? And maybe you can take a peek at the, let's see. Let's take a look at the skewness. Okay? Taking a look at skewness, it's positively skewed. Okay? So can you all draw that in the air? What would a positively skewed distribution look like? Let's draw one in the air. Okay, right? It means tail to the right, tail to the positive side. So on a number line, here's 0, positive, negative, so we have tails to the right, okay? And so we can see that we have some skewness, and there are different ways of computing skewness. We can compare the mean to the median, and we can see that this is what we would expect, right? The mean is a higher value than the median. What was our mantra from yesterday on thinking about skewness and the mean? The mean chases the tail. The tail is out here to the right, okay? So the mean should be further out than the median is. Are people following how that goes? Okay. So if it were further out there, and we're plotting age on this axis, and we're plotting frequency on that axis, then we would expect to have the mean further out than the median, and we're getting a mean of 22.79 and a median of 22. Does that strike you, by the way, as a relatively early age for okay, right? So I don't know if anybody in this room is 22, but you're probably getting pretty close if you're not already at 22. So back in 1993, had you been 22, wedding bills would have been in your near future as a statistical statement, right? Something like that's the median group. Now, of course, this is for married people. And you also have to remember that they're surveying a lot of folks back in 1993. They're not just surveying college students in 1993. So some of the folks in their sample might have been in their 90s in 1993. Some of them might have been in their 80s. So back in the early part of the 20th century, people got married generally a lot earlier than I think we are today. Okay, so it's skewed in that way. Okay, so you get the idea. And then can we dial all the way down and take a look at that? And people are getting that histogram. Okay, so superimposed here, we do have the Gaussian distribution. Okay, that's what a perfect Gaussian would look like. And these are what the actual data look like. Okay? And the perfect Gaussian, by the way, is what we might call a continuous distribution, which is to say that there's infinitely small margins between that point and that point. You can just make it smaller and smaller and smaller. Here we actually have plotted what we might call a discrete distribution. We're basically capturing the different ages in 1 year increments. Okay, so we might say that somebody is 20 years old or 21 years old, even though time is actually a continuous variable. We're sampling there in a discrete manner. Okay, and you can see that we have the tail going out this way. There are some folks who are getting married for the first time at what looks like, how would you estimate? What is that age approximately? Maybe 58 years old. Okay, so some people are getting married for the first time at 58. Some are getting married for the first time, mid-50s. We have one person down here, or maybe that's two people, I'm not sure, who's getting married at age 13. Okay, so at least that was true in that sample. You can see how these data are skewed. Okay? So we've now taken our first frequency distribution. I know we did this in research methods also. A lot of our students find this to be intriguing. When were people getting married? Now, what's interesting also about this is we had 1,500 people, right, in our sample, but not all of them are married. So if we just dial back for a moment, maybe you can join me back here. Okay, we probably get something like, probably tells us somewhere along here how many people were in the sample. So there are 1,202 valid cases and 298 missing cases. Okay, can somebody just unpack that for us? Why are some cases, quote unquote, missing or invalid? We're sampling randomly across 1,500 people in the country. Okay. What's the? Yeah, thanks. Okay, they could be not married, or maybe they are married and they didn't answer the question. You send out the survey and you get what you get. Okay, right? So maybe they didn't answer that question. Maybe they thought about it, but they're not married. Okay, So two of the 1,500 folks, and I think we can do that in our heads, 1,202 plus 298 adds up to 1,500, right? Okay. So of the 1,500, 1,202 were married at the time of this survey, and they provided information on that. Okay. Kind of interesting to think about kurtosis, 5.38. That's positive, so that's going to be slightly, or actually quite leptokurtic. Okay, so it's slightly heavier tails. It's hard to think about what heavy tails mean when the distribution is as skewed as much as it is. But anyway, if you ran through the math, it came out to be a positive value in this particular case. Okay. All right. So we've done now a frequency distribution in SPSS. We've made some contact with the GSS data set. And we'll pause there and see if we have any questions. Okay, so as we move on to our next idea, we're thinking about frequency distributions that can be skewed like this data set is. And we see in particular how skewed it is by looking at the comparison of the actual data to the superimposed Gaussian distribution. Okay? And that brings us to our old friend Gauss, who happened to be the first question on our TED-Ed data set. Okay? So Gauss gave us this, gave us that distribution. Why don't we flip over to TED-Ed, and we'll start going through some of the questions, and we'll see what kinds of responses people had. I'm over now in TED-Ed, and I'll go back to question 1. Okay, so we're talking about the German mathematician, and in one sentence, can somebody provide a fun historical or biographical fact about this founder of the Gaussian frequency distribution? Anybody want to share their fun factoid? Sarah's got one.
I remember reading that his mom didn't remember his birthday, so when he got older in his life, like she could remember what day of the week it was on, and there was 40 days in some sense, like relating to Easter, and so he figured it out doing calculations what his actual birthday.
Okay, so we have all different inspirations for doing what we do, and his mom couldn't remember his birthday. Okay, some other fun factoids. Oh, go ahead, Jake.
This is just from what I read. Apparently his wife was on her deathbed, and he wouldn't go visit her until he finished the math problem.
Okay, he's a man dedicated to his work. Okay. Go ahead, Shelby.
He didn't want his sons going into the field of mathematics or science because he didn't think that they'd do as well as him, so he didn't want them to.
Okay, so he seems to have known he was an outlier. I don't know if he thought about kurtosis. I think kurtosis is a newer idea. I'm not remembering the date of his birth and death, but I got the sense 1700s. It was probably right even there. There, 1755. Okay, so at that point, you know, when he was born, we didn't know about the Gaussian curve. He invented it, and then at some point later, he'll probably figured out, well, you know, that does a lot for us, the Gaussian curve. But what do you do with this age of married distribution, age when first married, that gets skewed and so forth? So he probably didn't realize, or he had some intuition that he was an outlier, and he felt that his children would not do as well as he would. Okay. Other ideas? Other fun factoids about Gauss? How many people have taken history and systems in psychology? Okay, I don't know if Gauss rears his head there. He's really not a psychologist per se, right? But so much of what we do, including z-scores, which is our top, depends entirely on the Gaussian distribution, which has a skewness of 0 and a kurtosis of 0, okay? And a mean of 0 and a standard deviation of 1. So those are the 4 moments describing the Gaussian distribution. Okay. Okay. So. Question 2, let me take a look at this. Take a look at the Gaussian distribution image shown on this site. Maybe I can go there. Okay, there we are. Okay. And I think the question was something like, what's clear or what's not so clear? Is that, I can go back and read that question, but I wanted you to take a look at this and see how busy it is, right? I mean, it's a nice looking curve, and then you put all these numbers on it, and it seems to get a little bit unwieldy. So identify some attribute of the image that you clearly understand, and in another sentence, identify something that's maybe not so clear, okay? So what's clear here? Anybody want to say or share what is clear to them?
Okay, thanks, Hannah.
I said the standard deviations along the bottom
Good, okay, and a z-score is a standard deviation, okay? That's a simple way of thinking about z-scores. A z-score is a standard deviation. So we can think about this as being one standard deviation above the mean, one standard deviation below the mean. That symbol that you see there, of course, is sigma, which is a population parameter. Okay, we typically use mu to refer to the mean and sigma to refer to the standard deviation. So we're one standard deviation shy of the mean, 2, 3, and 4. In principle, a Gaussian distribution goes out to infinity. In practice, that's not all that helpful. It's pretty rare that you would need to go out as far as 3. Usually by the time you've gone minus 3 to plus 3 on a Gaussian distribution, you've got almost everybody in your data set. So if in your practice, when you're doing statistics on whatever project you might have, if you go minus 3 to positive 3, almost everybody will be okay with that. Any reviewer of your work will be fine. In principle, though, it's a mathematical idea, so it can go off to negative infinity and positive infinity. In practice, plus or minus 3 is plenty. Often plus or minus 2 is just about everybody. Okay? Okay. How many people remember seeing from Psych 100 or Psych 200 this 34-34 business? Okay, can you just remind us what that is? What the 34s are telling us? It's probably really obvious, but maybe it's not.
Sort of the percentage of responses that were sort of within like one standard deviation of the mean.
Okay, right. And you can think of it simply as the area under the curve to the left of this boundary and to the right of that boundary. So between 0 and negative 1 standard deviations of any Gaussian distribution. It can be on IQ, it can be on height, it can be on physical attractiveness, it can be on anything that's Gaussian distributed, okay? That's just a mathematical property of this, right? Okay, right? Which is really cool, and it gives us a lot of generalizability. One of the virtues in science is generalization and generalizability, right? So 34% will always be the area under the curve for this. And then you can see there's a smaller percentage, smaller area under the curve between the first and second standard deviations away from the mean, and they are symmetric, 13.59, okay, because this thing isn't skewed. So what's ever true of the left side is true of the right side, okay? Okay. Then we get z-scores. It looks like they've also done t-scores. Remember doing t-statistics in Intro to Psych and also in Psych 200. And you can think about the t-values here. Okay. And then there are the other ways of describing dispersion. Okay. And you can talk about these stay nines, right? Okay. Standard nines, and just different ways of thinking about it. We will not be using these. I've actually not seen these in any of the things I've read, but you can imagine that there are lots of ways of divvying up this bit. What we're going to be using lots of times here is standard deviations, and that's our hero for today, standard deviations. Okay, let's go on to the Teton question number 3. The bell-shaped curve is said to be non-cumulative because, although it rises through the mean, the 50th percentile, it subsequently falls. Imagine what the Gaussian curve might look like if it instead continued to rise even after passing beyond the mean or the 50th percentile. Go to Draw To and draw this cumulative Gaussian curve. When you're finished, share that link. So we'll take a look at a few of these. How many people had an intuition about what that might look like? Okay, you had an intuition about that? Okay, and we'll see what this one student happens to have. Oops, can I go there? Okay, okay. So what's cool about this is this looks pretty linear, okay? And this is it's a chance for me to talk about something called monotonicity. So this is ever increasing, and all positively sloped lines are ever increasing. Negatively sloped lines are ever decreasing. Okay? And because they're always moving in one direction, they are monotone. And we talk sometimes about the monotonicity of a function. In this case, it looks like a linear function. And it is growing. What we're hoping to see here is something that is, the first half of it is shaped just like the regular Gaussian. And then instead of it doubling back on itself, it would go up and up and up, and then it would probably taper off or asymptote. Okay? Let's go back to the lessons. Let me go to somebody randomly selected. I'll go down here. We'll take a look at what Vanessa had to say. Here's Vanessa. Which question was that? 3? Hey, okay, that's about it, okay? And so you can see that if this were perfectly shaped, and she drew this much more effectively than I would have drawn this, so thank you for that. It's hard to get really smooth lines going here. Here's 0, perfect, right? So the first half of this looks just like the Gaussian, and then it continues to grow, but it tapers off. So we're growing at a decreasing rate, which is the parallel to what you have over here. Here it's increasing at very modest rates, and then all of a sudden it really takes off it continues to take off, and then it increases again at very modest rates. In principle, this goes off to infinity in both directions. In practice, +3, -3 is plenty. Often +2, -2 is plenty. Okay? All right. We cool with that? Love Draw2, and how lucky I was to randomly encounter one of the IT people out on the sidewalk just before the semester started. Okay? Lucky for me, perhaps not so lucky for you. And you may have heard the saying, you can't compare apples to oranges. In your own words, explain why z-scores allow us to compare apples to oranges. Anybody want to help us out with that? Why do z-scores allow us to compare apples to oranges? Is that a stretch, or is that a Jake's? Okay. Thanks, Jake.
Essentially, z-score is convert different measures to a standard score.
Okay.
And once you convert it into the same standard, you get the different rate.
Yeah, really good. Okay. And so this is an example I always use in research methods, and I think I use it in Psych 100. I'll use it here again. So height can be measured in such things as centimeters or inches or feet and inches. Weight would be measured in something like grams or kilograms or pounds. Okay. So I was out on my run the other day. And shortly after my run, I weighed myself, and I think I was about 125 pounds or something like that, maybe 127 pounds, in that range, okay? All right, that's a statement in pounds. I'm also, at least when I've got my shoes on, I'm 5'7", okay? So what I'd like you to think about is, we have these two different measures. We have feet and inches, I'm 5'7", and I'm about somewhere between 125 and 130 pounds, something like that. It's hard to know how to compare those two, feet and inches versus pounds, apples to oranges, okay? But we can convert all of those into z-scores. So knowing what you know about typical adult males, okay, is my z-score in height, given that I'm 5'7", is my z-score in height positive or negative? I'm 5'7"? I have a negative z-score, right? So the mean, whatever that is, and we can look it up, it's probably like 5'9" or 5'10". And there's some variation there depending on race, interestingly enough. But I'm of European ancestry, so for males of European ancestry, it might be something like 5'9" or 5'10", would correspond to the 0 z-score. If I'm 5'7", I'm down here on your left-hand side, okay? So I'm going to have a negative z-score. I don't know what would you imagine a 5'9" or 5'10" adult male would weigh, typically? Remember that college students tend to be a little bit leaner, right, than their dads, right? 160 pounds, maybe 160 to 170. Does that sound about right for maybe an adult male? 160, 170, maybe up to 180. Okay, so I'm at 125 to 130. Do I have a positive or negative z-score in weight? I have a negative z-score in weight. I have a negative z-score in height. Okay, right? So you can compare weight to height, even though those are different physical measures, right? You can imagine that if we had a Gaussian distribution of educational attainment, right, somebody who is actually as far as you probably are already more educated than the mean person is educated. Probably the mean level of education, if you counted just number of grades completed, and we think of 12th grade as 13th grade, if we count kindergarten, right? Okay, so 13 years of education, and then you can think of first year, second year, third year in college. We probably have juniors and seniors in here. You're probably greater than the mean. Okay, so you probably all have positive z-scores in educational attainment. I have a PhD, so I have a positive z-score in educational attainment. I have a negative z-score in height and weight. Okay, but we can actually figure out what those values were literally, and we can compare all of them. As Jake is pointing out, we have standard scores. We can compare apples to oranges. Wonderful. What a wonderful breakthrough Gauss has given us by being able to do this. Okay, really cool that we can get beyond the particular dimensions. Weight is in the dimension of pounds, right? We can have this dimensionless unit that is the z-score. It is dimensionless and allows us to make these comparisons. Really cool stuff. Okay, let's go on to number 5. Assume that the IQ distribution has a mean of 100 and a standard deviation of 15. And that actually is how these are typically quantified. Okay, people who study IQ will usually consider those as their parameters. The population parameter will be 100 for the mean and 15 for the standard deviation. What z-score is associated with an IQ of 70? Okay, some people can just do that in their heads. And sometimes when you can do it in your head, it's actually a curse, because then when you get to a more difficult problem, you actually have to figure out how to do that work. So let me go to a different student just randomly. Okay, we'll take when, and that was question 5. Go back to question 5, and we'll see if we can go to this. Okay, so, oh, good, you typed it out. Okay, so 70 minus 100 was 15. Okay, and so the idea is we come up with negative 30 divided by 15 is minus 2. Okay, all right. Who's following that? People okay with that? How many people did z-scores in Psych 200? Some people did z-scores in Psych 200. How many people did not do z-scores in Psych 200? It's actually not, we have a bunch of items that are required in Psych 200, and z-scores is not one of them. Depending on who your instructor is, you might have had this before. Okay? People okay with that? This computation is fairly straightforward. Probably for this group, that's really simple. Can we all get out the answer to this one? We'll go on to number 6. Assume that we have the same distribution. What z-score is associated with an IQ of 145? Can we yell it out? Why did the author pick 145? I wrote this question about 48 hours ago. Why did I pick 145? I'm sorry? No. Actually, my IQ is also negatively z-scored. I have an extreme IQ. It's 4 standard deviations away from the mean on the low side. So yeah, I'm way down there. Oh, so what is my IQ, by the way? If my IQ if I have an IQ that's minus 4 z-scores, what is my IQ? 60? How did you get that?
15 is the standard deviation.
Right, and we're going to multiply that by 4. Actually, it isn't 60, but 60 was a good number to get. Okay, 60 is half the way there, because 4 times 15 is 60. And what other trick do we have to do with 60?
Oh, subtract it.
Okay, so here's the mean, right? And now, so I'm down this way, and then I'm down this way, and I'm down this way, and I'm down this way. Right? But was there some other reason why I picked 145?
Isn't that like the standard cutoff for genius?
Oh, okay, it could be. I mean, that would have been a better reason, but, I'm a guy down here, so I didn't have such a good reason for doing it. I was just trying to pick a simple multiple so that you could do it in your head. Right? You probably can do 15 times 3 gets you to 145, and this group is very good at doing that kind of thing in their head. So I thought I'd come up with some simple multiples. Let's go on to another variation on that. What we want to get to today is that with using z-scores, we want to be able to move from z-scores to raw scores, and we also want to be able to move from percentile ranks to raw scores to z-scores. Okay, that's the other item that we want to put into the mix here. Okay? Oh, by the way, in case you're wondering why my IQ is 4 standard deviations lower than the mean, it's because I'm a really good test taker. Okay? And what I mean, you might be smiling about that, but you can imagine that my actual IQ is 5 standard deviations lower than the mean. But because I'm a really good test taker, I can actually bump my score up to just 4 standard deviations lower than the mean. Interesting concept. Okay, and we'll come back to that when we think about overestimation and underestimation when we're talking about any kind of standardized test. Okay, so off to question number 7 in TED Ed. Assume that we have the same distribution that we had a while ago.